Okay, so yeah, I think last time we discussed on power series, and basically the typical problems in power series is to know the convergences, okay? The radius convergences, and then the interval. Okay? How convergent our series will be, okay? Because in power series, the convergences is not only about one point, but it's about the some range of numbers, right? Okay. Okay. Related to this power series, remember that if we take the new page here. So if you remember that if we take the x power of n, okay. If we take this as a series, we can for a few terms we can write this starting from n equal 0, which is becoming 1, and then x, and then x squared, and then plus x power of n, blah, 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 right? Okay, and then we know that if the ratio between these terms less than 1, we can make the series converge, and we take the sum of the series as let me remind you the original formula. It's supposed to be a over 1 minus r, which is the geometric series, right? So this is a, this is ar squared, and so on and so forth. Okay? And r is the ratio. So based on what we have here, we can take the s by 1 over 1 minus x. Okay? Now this is to say that, well, imagine that if we start from 1 over 1 minus x, okay? If we let this as a sum, and we assume that this is converged, okay? The sum is converged, and let's say that this is just a regular functions, okay? We can then represent these functions in terms of series, okay? Okay, I hope you get my point. So we could take this and make the series out of these functions, which is 1 plus x squared plus or you could simply take this series x to the power of n, and simply you could just take a look at these functions, and you could switch, okay? You could revert these functions into a series, okay? Which is very intuitive, okay? And later, we are going to see that it's going to be useful at some points. Okay? As long, maybe let me write here, as long as the ratio or the x, okay, is less than 1. Right? The assumption for to be converged, right? This is to be converged. And of course, because this is not really prove anything, right? Well, we could take limit, okay, to make things more clear. So we could take the 1 over 1 minus x equal, let's take limit, and let's take a partial sum. Let's say the partial sum is denotes by Sn of x. Okay, this is the partial sum. So what we are going to do is we are going to look and take some few terms, for example, when n equal 1, n equal 2, n equal 3, and see how the graphs will look like. Okay. So let me go here. Okay, this is the point that I am trying to say at the beginning. The title for this section is the representation representations of functions as power series. This is the title. So the idea is to represent a function and then rewrite the function as a series. Now, of course, if you check using your graphing calculators, you can check the graphs for 1 over 1 minus x, right? Now, we could take this and let's say we are going to check with a few terms, okay? For example, when n equal 1, this is going to be just 1, or this is 0. So 0, and then 1, 2, 3, and so on and so forth, okay? So we are going to check the s, let's say s1. So s1 is 1 plus x, okay? s2 is 1 plus x squared. s3, 1 plus x squared plus x cubed. And then let's see how the graphs will look like. Now if you take the graphs, let me make it more bigger. Oh, maybe let me write into the left here. Let me take here so that you can observe the whole paper. Okay. So you can see that our functions here, the red color here, okay, and perhaps at some point because of the property of each curve has some little bit differences, but it's not that significant. But what we are going to focus on is we can see here. Okay. So as you see from the x2, when we increase the terms, okay, it's going to take the interval getting closer. The gap between the partial sums is getting close to the f. Okay. So when we add the terms, for example, s, maybe s100, maybe it's going to be like nearby this f. And remember, the number that you put, it will not be exactly at this f. Okay. That's why we need to take the limit. But using limit, then this two terms getting closer together, and we can take this as I think intuitively prove what the representation functions here, okay, and then we can refer these functions as a series. Okay. So whenever you see any functions, that you can extract the functions and make the functions in terms of 1 over 1 minus x, then you could definitely find a series. Okay. Well, if you're interested to check, I think you can try on the GeoGebra or Desmos and try with the more functions into here and maybe take into some numbers. Or if you are maybe input in the Wolfram Alpha, and you can check through when n is maybe 100, 1000, and so forth and so on. Or if you want to, not sure, I think you could create some simple, simple programming, but it takes time. I think if you want, then you could check. But I think some software we can just input the formula, and then they can compute with some with our inputs, right? I think you can try. Now AI is everywhere, so you could check that out. Okay, and I hope you can learn using that tools. Okay, and don't rely too much on AI. They can help you, but at some points, but of course, the brain is your brain. The main brain is your brain, not the computer. Okay, a few quick examples to see how we can use this formulations into our solving problems. Okay, so let's say we are having 1 over 1, let's say plus x. Okay, now the idea, okay, every function that you may find, if you can extract this form, then we can try it. Now the problem is this is having plus. Now just change to minus minus, right? And then exchange all the terms. So if we could change this and make this into 1 minus x, all the things we are going to see will be, well, let's say this is going to be 1 and then minus x, and then or if we look here, okay, we look closer here, we change x into negative x. Okay, so maybe let me write with plus first. Plus negative x like that. Okay, plus and then negative x squared. Okay, and plus x cubed and so on and so forth. Okay. Yes. So you get the whole idea. So when we take, for example, we take the some variations here and maybe take x squared like that. Then same thing, we take 1 minus and then minus x squared. Okay, so we change the x into negative x squared. So what we are going to do is we take 1 plus, now the inside is now negative x squared, and plus negative x squared squared, okay, and then plus negative x squared cubed, and so on and so forth. Okay. And of course, after you did this, the next thing is to make the series. Okay, to make the series. So series sum. Let's say it's from n equals 0 to infinity. And since I will have 1 minus x squared plus x4, right? And then minus x6 plus x8 and so on and so forth. We see that we have the alternate signs. So we have negative 1 power of n, and then x now becomes with power of 2n, right? You could also do the same thing with the first one here. 1 negative x plus x squared, negative x cubed plus x4, and so on and so forth. And perhaps this is going to be sum, same alternate signs, and then yeah, this is just a normal x with power of n. Now another example, still same 1 over 1 plus x, that is our 1 over 1 minus x, that is our core. So if we have, for example, we take 2 plus x. Okay, so the concept, we need to force the formula into the 1 over 1 minus x. Okay? So we are going to factor out 2 because we want to make 1 plus something. Okay? 1 plus x over 2. And x over 2 is the one that we substitute into the series, right? And this is going to be 1 over 2, 1 minus x over 2. So the series will be multiplied with a constant 1 over 2. So 1 over 2, and this will be the series. Okay. And the way we take the series is similar with this. We change the inside with negative x over 2. Okay. So when you learn and you get the idea to change the whole thing, the x with the substituted here, I hope you get the logic behind that. And after you got the terms, then you need to find with the series, okay? With the sum and then some form here, and then that's your series. Sometimes the final result here will be having alternate results, and then that's okay. As long as it's true, that's okay. And perhaps the question is not only to find the series, but maybe asking the power series questions. The radius, and then the interval. But it starts with the functions. It starts with the functions, and then maybe it's asking to find the series, find the radius, and then find the interval. So it's combination from the previous one. Now, for example, after you get the idea, you could directly write this, and I hope you get how does it come from, where does it come from. So this is half the constant, and then I will directly write sum. Since x is changing to negative x over 2, and the negative means that it will be an alternate series, so I will write negative 1 over n, or maybe let me write the basis first, which is the negative x over 2 power of n. Okay, if you want to stop here, that's okay. But if you want to make it more clear, to show the alternate signs or the alternate series, or you want to combine the half, the constant. If you want to combine this constant inside this, that's also I think you can do that as well. So we can just write clean in terms of the sum. Right here, it's supposed to be here, there. Okay. And then the alternate series, and then This is 2 with power of n plus 1. Okay. Plus 1 is from the constant. Okay. And then x with power of n. Okay. It seems more complicated, but I think you can just stop here. It's still okay. For me, still okay. If you're more clean in terms of series, and then I think it's really clean answer. Okay, any questions? Any questions? Okay, I hope you get the step-by-steps clearly. So always goes back to the core formula, 1 over 1 minus x. That's the core formula. That's supposed to be a series of the x to the power of n, x power of n. Okay, I think we have more time. We can have more review on this, but let me go through the next one, which is still in the power series. Still in power series, but this is going to be, we can take derivative of the series, or we can take the integration of the series. Okay. For example, let's say we have this power series x minus a to the power of n, and c is a constant. Okay. If the convergences or the radius is positive radius, which means it's there, which means we have the interval of convergences, right? If we write the functions, if we take the terms, okay, from 0 and then 1, 2, and so on and so forth, and then we say that in this theorem, these functions here, or the series in a whole, is we can derive this series. Okay. It's differentiable, and because it's differentiable, of course, it's supposed to be continued on the interval of convergences. So we could take the f prime, the derivative, and the integrations. Okay. So if the function here is differentiable, we can derive and we can integrate. Okay. And both the derivative versions and the integrate versions, they have the same radius, which is r. So how does this theorem imply? Okay. Which means if you know the functions and you think that maybe we could extract something from that functions, remember our core is 1 over 1 minus x. Okay? Imagine that there is another function that is derived from that 1 over 1 minus x. Or maybe the integrated version of that. So one way to take that is either derive the functions or integrate the functions. Okay? Let's say, maybe right here, maybe here. Okay, let's say we have 1 over 1 minus x. Okay. Okay, if we take derivative of this will be 1 over 1 minus x squared. Oh, maybe let me write the whole questions. Let me write the whole questions. So express 1 over 1 minus x squared as a power series. Okay, and then to solve this, we could take the let me start with the 1 over 1 minus x. This is 1 plus x squared plus and we could take sum. Okay. If we differentiate this, okay, so take derivative right, and then this will be 1 becomes 0, so I will not write 0. X become 1, 2x squared become 2x, and then x cubed become 3x squared, and so on and so forth. Okay. Now if you look closely, this is become 1 because it raised 1. It's shifted to the right 1, so n is started from 1, and then this will be n x n minus 1. But if you want to start from n equals 0, you can also do that, and you could simply just plus 1 the n, right? So you could write n equals 0, which means you shifted the n, right? You could write n plus 1 and then x power of n. So the idea is still related to this 1 over 1 minus x. So either we differentiate or we take the integration, which is, if you see this is 1 over variables, we are going to have log, right? If we integrate. So that's another possibility that we might have. At least for now, okay, for now. So you derive and then you could integrate, okay? Okay, maybe if you're still writing the notes, let me wait for a moment. Okay, so let me go through another template here. Let's say the functions is ln 1 plus x. We know that this derivative is 1 over 1 plus x, okay? And we know from the previous slide that this is going to be 1 minus x, which is 1 minus x plus x squared minus x cubed. Okay. So in this case, we could write the ln 1 plus x as a result of the integrations of 1 over 1 plus x dx. Okay. Now we could integrate the whole summations. So 1 minus x plus x squared minus x cubed plus dot 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 dx. Okay. Now integrate 1 by 1. 1 become x. Negative x become negative x squared over 2 plus x cubed over 3 minus x with power of 4 plus dot dot dot, and then don't forget to plus the constant at the very end. Okay, at least this part we can take as a series. Okay, since it's alternating, and you can start from n equal 1, n equal 0, it's okay. Let's start from n equal 1. N minus 1. Okay, so 1, okay. This sign is okay, and then this will be x with power of n over n, and then plus constant. Okay, we still have a constant here. How do we deal with this constant? The easiest way is check the x. Remember that this is ln 1 plus x. Okay, so let x equal 0. Okay, to make all of the ln become 0, ln 1 is 0, right? So we take this ln 1 plus 0 is equal to, when x is 0, then the whole thing is 0, the series 0, right? Plus constant, right? So which means that the constant is 0. So we could erase the constant. So the conclusions is ln 1 plus x is equal if you want to write the ratio is less than 1, it's also okay. Just to confirm that this is convergence. Yeah, there's still one more example that I think we can take the example as a typical formula. So we see 1 over 1 plus x and then squared. We see the ln 1 plus x, and then the other possibility is the tangent inverse, the arctangent. Because the arctangent, it has relation with 1 over 1 plus x squared, right? And we know 1 over 1 plus x squared, we can take that into series as well. Okay? So let's take the example here. Okay, let's take g as a tangent inverse, and we know that if we take derivative of g, we got 1 over 1 plus x squared. Okay, so we could take the tangent inverse as a integrations of 1 over 1 plus x squared dx. Now previously we know that this 1 plus over 1 plus x squared is 1 minus x squared plus x squared power 4 minus x power of 6 plus, okay. So we could take the integration of each one of them. Dx, okay. So x minus x cubed. Well, you could start from the constant at the beginning if you want to make your notes clean. So c plus x minus x cubed, and then plus dot dot dot. And then we take the series into summations. Let's say it's the bottom one is from 1, 3, 5, 7, which is the odd numbers, to n plus 1. And this one will be x to n plus 1 as well. Well, the constant, we can erase the constant because we could let the, well, let's just say x equals 0, and then you could see how it goes. So tangent inverse of 0, okay. And then this will be all 0, and this will be a constant, and this constant is 0, right? So I think this is 11.9, the representation function as a power series. After this, we are going to see the applications for the derivative and integrations that in this representation, which we call the new series, the Taylor and Maclaurin series. Okay, that will be the next section. So after we finish that part, then that is the whole content for midterm, okay, until the Taylor and Maclaurin series. Okay, so chapter 10, 11, okay, until the Taylor and Maclaurin. We haven't yet going to the Taylor and Maclaurin, but the content will be until that part. Okay. And then what else? Oh yeah. I think to make sure that our schedule is okay, then perhaps the midterm will be, I think the safest schedule is 20, okay? April 20. So if we finish the chapter, we can have a little bit review and move to the next chapter. Which is 12 and 13. Okay. Chapter 12 will be very short because I will skip much of the sections because that is vectors. So I think you already have more courses on vectors before, so I will skip some parts that I assume that you know, hopefully. But if not, I will prepare some additional content for you. And chapter 13 is basically similar techniques with calculus 1, but how we write in terms of factor. But the calculation will be no different than the calculus 1. The difference is just the how we write. That's the difference. The style is in the factor. Okay, that's chapter 13. And then after that, we can go to chapter 14. Okay. So I assume after 12 and 13, I think 1 week we can finish the chapters. Okay. Okay. So 20. Okay, April 20th. Okay, midterm. Actually, we could take midterm next week, but I think too soon. Too soon for me too, because I need to prepare the question. Okay, maybe we take some of the example here. Okay, maybe I will give you 2 questions. So write in a power series. So write in a power series the given functions Okay, let me give you some time to try. Okay. Notice that both have the x on the numerator. So which means that the form can be multiplied with a constant x. Okay? Constant x can be extracted outside of the sum. But of course, you need to find the relations first. So anyone got the result? It's thing. Especially the second one is really long. So let me give you some hints how to look at the question. So first is this functions. We have x over 1 plus 4x squared. Remember, our core principle is always in this chapter, in these sections, is always from 1 over 1 minus x, right? Okay. If not, then derivative of it or integrations, right? So the first thing is when we look at the structure, we see that x. Can we have something x from this derivative or the integration? No, right? Which means that it's a separate entity. So we could think only 1 over 1 plus 4x squared. That's the first thing. Okay? So we could write this in terms of, so let me just write x here and then write the whole thing becomes that. Okay? Okay, now, of course, from the principles, we can say, let's say we are going to look at the 4x like that. Okay, if we looking at this terms, okay, let's say we have this. Okay, and if we would like to know the relations, I think we could think one possible way is to derive that. Right? To derive. Okay, suppose that we have this 1 over 1 plus 4x. Okay, then perhaps if this is our let's say f, or maybe h, let me write h. If this is h, then the h prime, if we take the derivative, if you would like to check whether it's in our derivative or not, then this will be well, you could think from here, right? So it's supposed to be negative in the front, so negative 4 over 1 plus 4x squared, right? Okay, now we got the one that we are looking for. Okay, we are looking for the denominator, right? We are looking this part. Okay. Okay, so what we can do? So either we can start from the original, the right here, the 1 over 1 plus 4x first. Okay, we check this series. This is 1 minus 4x, right? We can start from here, which means we can take this sum and just exchange x with negative 4x with power of n, right? And then we take the derivative. Okay, so this is h, and then if we want to know the series for the derivative, then we are going to derive. Okay, derive the sum. Okay, so derive. So let me give the idea here. So derivative. So this will be n x n minus 1, and we have negative 4 n, right? Or we could write negative 4 okay, the same thing. Okay, at least we got the derivative. Now, the final results. We are going back to look at this function here. Okay. So let me write again. The functions of f is x, and then multiply with the 1 over 1 plus 4x squared. Okay. And then we can exchange. So this is x. This is h prime, right? Or maybe I think we can directly write from the first here. So let me. Okay. But this is negative 4. So we need to multiply with negative. So negative x over 4 okay, because what we get if we derive, we have the negative 4, right? So to make into our original source, we need to multiply with negative x over 4 to make it into the original questions that we are looking for. Okay. So the final result is the series of this multiplied with negative x over 4. Okay. So negative x over 4, and then this series, write all the things here, and then n plus 1 x power of n. Or if you would like to separate this negative 4, become negative 1, you could do as well, but I think we'll just stop it here. But if you want to make it more clear in the terms of series, I think still okay. I think this arrow is confusing. This is supposed to be the negative 4 here. No, this is just changing this into this. Okay. Shifting the n. That's the same thing. The same thing. Oh, wait, you're right. Right. This is supposed to be 1. Because it's derived. I forgot to. because it will be right, which means it's shifted. The n is shifted. And then I convert back to n equals 0, which means we plus 1. Okay. Hope you. I hope you get familiar with the sum. Okay, if you are shifting from 1 to 0, which means all the n need to plus 1. Okay, need to plus 1. Okay. So from this 1 go to the 0. So it needs to take this whole 1 that is the plus. Okay. So n becomes n plus 1, n minus 1 become n. Okay. This n become n plus 1. Okay. I think also to check whether your series is correct or not, sometimes if it is easier to make a terms, I think you could check a few terms, maybe n equal 1, equal 2, equal 3, check whether it makes sense or not. If not, maybe there's something wrong in the equations, that maybe some miscalculation or maybe some maybe different assumptions. Okay. Okay, the second question is a little bit complicated, but let me start with this. Okay, if we want to make this into this cube, okay, first we could rewrite this and make this into our consideration. Okay, so we could see that if we want to focus on 1 over 1 minus x and find any function that has a possibility to be related with this 1 over 1 minus x. Okay? So you need to find his family. And I think x cubed is not his family. So we can kick out the x cubed and we focus this 2 minus x cubed. Which is, I think, for our work before, we learned that whenever we find some square, cube, or maybe with power of 4, it means that perhaps we need to derive. Okay? We need to derive. And the first trial that we can try, or maybe the functions that we can try to derive is 1 over 2 minus x. Okay? Let's say this is our function. Let's say function k. Because if you wanted to find the derivative, this is become 1 over 2 minus x squared, right? And then k double prime, we are going to find 1, or now it's 2, because it goes to squared, move to the front with 2, right? So 2 okay. Now this is what we are looking for. This denominator, right? Now, after we find the relations that this is what we are looking for, then we need to find the series. I think this is easy to find, and then you derive, and that is the series that you're looking for. So take times. So we can start from this part, 1 over 2, 1 minus x squared, x over 2, sorry. This is half. And as I mentioned, we can write in a more clean, or maybe a little bit right, x power of n divide 2 n plus 1. Now the derivative, we derive the series. Okay, now we derive the series. Derive the series. Now it's shifted to 1. So this is going to be n x n minus 1. And remember, the 2 is just a constant, so we just keep 2n plus 1. What we derive is x, not n. And then derive one more. Now it's become n equal 2. So n minus 1, x, n minus 2, right? Still same. Here is 2 of n plus 1. Okay. Now, if you want to make it from 0, then we shift it 2. So we plus 2 to each n. So n plus 2. N plus 1. And then n. Okay. And then this will be n plus 3. Yeah. You need to be slowly but steady. Okay. Do not rush writing all the things. Okay. Because if you make mistake at the middle of, or maybe at the early process, then it will be very difficult to follow the form. Okay, and then since this is having 2, then we need to multiply the original functions with this constant. Okay. So the original k, or the original function is what? G. G is x cubed multiply with this is supposed to be 2, so to make it 1, so we need to divide by 2. So 2, and this part here we can replace with the series, this series. Okay. Okay. I hope you can finish the final result. Okay, just replace the entire 2 over 2 minus x cubed with the whole series here. Just replace with that. So one of the important point within this representation functions is to find the relations. Okay? To find the relations, derivative integrations from the functions. Now, if you're still struggling finding the derivative and the integrations, I think you need to check other sources for additional contents. Okay. I think I've given you some examples. Okay. And I believe there are many sources in the internet, so you could find. And even within your own language, I think that will be better. But I'm suggesting find with the English terms, okay? So you know at least the terminology, the English terms. But if you want to maybe take more time to digest, then you can find your local source within your own language. I think there are a lot of tutorials and everything. Because sometimes I also watch those tutorials and see how to construct the idea. And yeah, the more to come is need to have like making like reading, find source thing that will be, I think in the near future will be, and I think it will be very useful for your habit. Okay? So more reads, any articles, news. Okay. Because we sometimes get distracted, right, with social media and so on and so forth. Sometimes we lose focus, and I think that's the problem, okay, within, I think, today's generations. Okay? I see we have a lot of information, but we are losing our focus. I think that's one possibility why we have difficulty to analyze the problems. I think that's one of the main reasons. Okay. Okay, any questions regarding this? At least if you keep to the core principle, 1 over 1 minus x. Okay? That's it. That's the core principle. Everything is related to that 1 over 1 minus x. Okay? But how you relate that is, yeah, it takes time and takes some probably practice. Okay. Okay, yeah. It's two? Yeah, from here. Yeah, you can check from right? Just go. Okay. Press your profile. Okay. Now I would like to introduce you to the Taylor series and Maclaurin series. Yeah, this is the I think the difficult part in this chapter. So let me go through. Okay, let me start with start by a function, or maybe let me write the title first, Taylor and Maclaurin. And they are the founder for the series. There are two different series, but they are actually similar in some sense. You'll see what the difference is later. Okay. Let's start with taking some functions. Okay, let's write the functions in terms of the series that has convergences, some radius. Okay, and it's centered at A. Okay, it start from C0 plus C1 This is another form of the power series that we previously discussed. Okay, let me write. I think I need until 4. So C4 x minus a with power of 4. And then the ratio, which is the x minus a, is going to be less than r. Okay, if we put x equal a, which means all the terms will be 0. Okay? So fa is going to be equal to the constant, okay, constant 0. Okay, now the functions, try to derive. Okay? So f prime x, so the constant becomes 0, and c1, so x minus a, x become 1, so it's become c1 constant, and then plus 2 c2 x minus a plus 3 c3 x minus a squared plus 4 okay, and then plus dot dot dot. Still radius the same. And the substitutions will give you C1, okay? If you substitute the x with a. Now let's do this until the third derivative, okay? To see the relation. So take the derivative. So this will be 2c2, okay? And then x, oh no, this has become 1. Okay. And then the next part is 2 multiplied with 3, and I will not multiply, become 6. You will see why. And that's the c3 x minus a, and then plus 3 multiplied with 4, c4 x minus a squared plus dot dot dot. Still the same radius. And then the same thing, we put a into the second derivative. This will equal to 2c2. Let me write this that one. Okay. Now take another derivatives. So third derivatives. So this will be 0, and this will be 2 multiplied with 3 c3 x minus a plus 2 multiplied with 3 multiplied with 4 c4 x minus a, right? And then you could guess what's the next term. It's 3, 4, 5, right? And then c5, and then x minus a, and then square, right? If you see the pattern, you could guess what's the next term. Okay. And then the same thing, we take a into the equations, and we get, oh, why I'm right, this x minus a, sorry. So 2 by 3 c3, or we could write simply say this 3 factorial 3 factorial c3. Okay, now let me move this first. That's the conclusions. Okay. Okay, so the patterns gives, so if I write f, if we derive how many times, how many n's, okay, the time we derive is going to be equal to 2 multiplied by 3, 4, until multiplied with n, cn, or we could write n factorial cn. And the coefficient n, we could simply get the conditions n factorial. Okay. The f with this n means the derivative, okay? The derivative terms. Okay, so you could get this one here. Let me write the right side. Okay. And then the second part, if we substitute back the Cn into the main formula, this is what we have. So we could describe this in the terms when n equals 0, 1, 2, 3, 4, and so on. And this becomes some series. Okay, it's become a series. Now this is what we call the Taylor series. So the Taylor series, if you increase the terms, if you increase the n, 1, 2, 3, which means that the functions is getting more derived. Okay? So the first derivative, second, third. So the more you increase your n, the function is getting more derivative. The first derivative, and the second derivative, the third derivative, and so on and so forth. So you will be given a functions and find its Taylor series, for example. Maybe given a equal some numbers, and then you can input into the series as well. The Maclaurin series is actually the Taylor series with a equals 0. That's the difference. Well, I think I will be focused on the Maclaurin, I think next week. I will, I think, stop until here for today's class. So hopefully you can have more review at least the calculus 1, okay? At least for some basic derivative and integrations. Because I think in this series, especially the Taylor and Maclaurin, you will need to find the derivative a lot. If you see from the previous page before, you see that we also have a problem with the derivative and integration as well, okay, when we relate the functions and power series, right? Okay, maybe before the class ends, any questions first? And before we go to the feedback as usual? How was your holiday? Is it okay? Boring? No? Okay. Okay, I think we can start the. I think before we start the feedback, let me show you. I think one or two sources that I found. It's pretty intriguing. So if you are, well, probably you are still in the in the freshman, not really into like research, but any type of research you find, any topics. This website is called the Connected Papers. It will connect papers with another papers, and they have the I think some machine learning inside, and it will create something like this. Okay? So if we see this one here, is creating this beautiful graph that is connecting all the papers, and I think really useful. So you can look for any topics you want, and if you want to find in a more scientific reference, it will give you some good results. There are others tools like this, and I think I found almost 10 like this one. Okay, is one of 10, but I think this one is for me the interface is good, and I think it's easy to use. And another one that I found really useful is this. It's the SciSpace. So, and this is, they include the AI robot inside. So for example, I will just take example here, maybe here. So this is giving you the short version. So it's even shorter than its abstract. And then if you see the right side, it has the Copilot feature, which if you familiar with Copilot, which means it's the AI. Okay? So you can ask everything, and even you could instruct this Copilot to do something for you, write something for you. So for example, they give you some, maybe if you want to ask like the definitions, okay? Maybe explain the abstract in 2 lines. Okay, and then explain practical implications. Okay, it's asking, and then it can generate. So this tool makes your if you find, and I know that for undergraduate students, if you read research papers, maybe from your senior or maybe from your maybe if you're senior, maybe the words sometimes difficult, right? Especially if you don't really know the English terms. If you are using tools like this, we could ask everything, even the basic definitions we could ask, and it can provide you some context. Okay, I think that's just I think just additional. If you want to know more, because I think everything now becomes more giving context to AI. Everything will be having an AI. Even when you write something like your Microsoft Office, they have now AI. So if you write something, this has like suggestion how to write. And if you like, it has if you check, I'm not sure whether you are joining the beta test for the Microsoft. They have those kind of features now. They already developed. Okay? So if you're not learning that way, we are going to lose the tracks. Okay, and I think this is helpful if you want to learn more in depth for some topics. Okay? And eventually, if you want to learn more like details, and you want to learn maybe trying I think everyone talking the ChatGPT, everything, right? That is just one thing, okay? And AI is more just than ChatGPT. Okay, feedback time. Okay. What do you think about the online assignment? The online assignment?
I was surprised.
Surprised?
Yeah, because I was checking if I had homework for another, then I see a cut.
It's not a quiz, it's just a
Yeah, I consider quiz, but small percentage quiz. Small percentage. But we can say it's quiz, but small percentage.
I didn't lose a lot.
Okay, I think we could go on. Okay, what do you think about the online test? Anything difficult? Some parts, right? I think some numbers difficult. Worst? Wow. If you haven't taken, you still have a chance until tonight, okay? Until tonight, if you haven't taken the test. I've extended the time. Because I know if you are in a vacation mode, maybe you're not opening any internet. Maybe you're focused on holiday. It's kind of hard. Okay. Disaster. What kind of switch? Okay, didn't find it. You can find it in the Moodle. You can find it in the Moodle. Check the weekly schedule. Okay, I think I mentioned the test on the Moodle. Check on the weekly schedule. Confused? Okay. Okay, so I start. Okay. Okay. Don't forget to write your student ID. But let me know if you win or if you have it in the you get into the top 10. Let me know your name or at least in the student ID. Okay, let's start. I hope enough time. Two minutes. 2 minutes. Just do exactly the same as usual. Just do exactly the same as previous example. Okay. Remember to find the R, take the ratio test. I think if you do it I think you can do it in your head. And plus one, right? Q. And move here, and Q, cancel. Right? I think you can do it in your head. Plus one, and so the n is cancelled, right? So you could get directly the answer.